So in this example, we're looking at x of t that is equal to this periodic triangular wave. Okay. So you can see here again that the signal is periodic with period 4, and therefore the fundamental frequency is again pi over 2. Okay. Now let us denote the Fourier series coefficients for x of t as, let's say, ek. Okay. All right. And suppose that we set this g of t that we obtained in the previous example, okay, as something with Fourier coefficient dk. Okay. Now notice that g of t is actually equal to the derivative of x of t. Okay. So you can see that for t from 0 up to 2, okay, for x of t from 0 up to 2, the derivative is minus 1/2. Okay. And for t from 2 up to 4, the derivative of x of t is minus 1/2. Okay. So indeed, g of t is equal to the derivative of x of t. Now, by this property here, we know that if you have a signal that is equal to the derivative of x of t, then the Fourier series coefficient of this signal, this new signal here, will be equal to jk omega naught times the Fourier series coefficient ak of the original signal x of t. Okay. So in our case, the original signal has Fourier series coefficient ek. Okay. So therefore, dk is equal to jk omega naught ek. Okay. And omega naught here is pi over 2. So this is just jk pi over 2 ek. Okay. Now for k not equal to 0, okay, I can divide this jk pi over 2 to the other side so that ek is equal to dk divided by jk pi over 2. Okay. And this dk we just derived in the previous example, right? So this dk is this expression here, right? So therefore, this is given by okay, so for k not equal to 0, it is this thing here. So this is given by, if I bring this 2 up here, I get 2 times sine pi k over 2 over j k pi squared e to the minus j k pi over 2. Okay. And for k equal to 0, right, for k equal to 0, E0 is just equal to the average of the signal over one period. Right, so this is just x of t x of t dt over one period, which is 1/2. Okay. So using our knowledge of the Fourier series coefficient of g of t, and by applying the property for differentiation, we readily obtain the Fourier series coefficient for this x of t, whose derivative gives you the signal g of t in the previous example. Okay. Now let's move to this next example, which is called a pulse train. Right. So here you see that x of t is equal to a delta function equally spaced by capital T. Okay. The summation of delta functions or impulses equally spaced by capital T. Right. So it is something that looks like this. Okay. So this signal here is sometimes called a impulse train. Okay. Now you can see that this is a periodic signal, right? Periodic with period capital T. So you can write it in terms of its Fourier series representation with the set of harmonically related complex exponentials that are all period with period capital T. Okay. And the coefficients AK you can obtain by 1 over t, the integral over one period. Let's say we take minus t over 2 to t over 2. This function delta of t. Oh, well, actually, okay, actually, this would be x of t e to the minus jk 2 pi over capital T dt. Okay, but over this one period, x of t is just delta of t. Okay, so I can replace this with delta of t okay, and when you take the integral over this, right, you have this inside is non-zero only when t is equal to 0. So when you substitute equal to 0, this is 1. So the integral of this is just capital T divided by capital T is 1. Oh, sorry. Sorry. Okay. So like I said, this inside is non-zero only when t is equal to 0, right? So when t is equal to 0, this becomes 1. So you have 1 over t, t over 2 minus t over 2, delta of t dt, right? So I'm substituting 1. I'm substituting this with 1 because it is non-zero only when t is equal to 0. Okay. And then the integral over a delta function, it has unit energy, unit area, right? So this integral is 1. So we get AK equal to 1 over t. And this is true for all k. Okay? So this is saying that I can express x of t as as 1 over t e to the j k 2 pi over capital T t for k from minus infinity to infinity. Okay, or you can bring the 1 over t outside since it is the same for all k. Okay. All right. Now, suppose we revisit the problem of finding the Fourier series representation of this periodic square wave. Okay. So suppose you're asked to find the Fourier series coefficients of the signal g of t. Okay. Now this signal g of t, although it may not appear so obvious at first sight, but this signal g of t is actually inherently related with the impulse train that we just described. Okay. And this is because if you take the derivative of g of t, you will get a signal q of t that is equal to the summation of two impulse trains. Okay. So if you look at this, you will realize that this q of t, which is the derivative of this periodic square wave, is equal to the summation of two impulse trains, one shifted to time minus t1 and the other shifted to time t1. Okay, so you have x of t plus t1, where this x is the impulse train that we gave on the previous slide, minus x of t minus t1. Okay. Now, by letting the Fourier series coefficient of q of t be denoted by, let's say, bk, okay, then this means that bk should be equal to, okay, should be equal to this ak times a phase shift because of the time shift in the time domain signal. Okay, so this bk should be e to the j k omega naught t1 because of this time shift times ak, which is the Fourier series coefficient of this impulse train. And similarly for the second term, I have a phase shift e to the minus j k omega naught t1 times ak again, which is the Fourier series coefficient for the impulse train. Okay. And then if I substitute this ak inside, I will get 1 over t 2j sine k omega naught t1. Okay, so if you recall, ak is this 1 over t, and these two the subtraction of these two complex exponentials give you 2j sine k omega naught t1. Okay. Now, by letting by letting the Fourier series coefficient that we want to find be denoted by ck. Right, so here our goal is to find the Fourier series coefficient of g of t, which we denote by ck. Okay, so we know that q of t is the derivative of g of t. So this means that bk should be equal to jk omega naught ck. So therefore, again, for k not equal to 0, we can write ck as bk over jk omega naught. Okay. And by substituting bk inside, I get 2j sine k omega naught t1 over jk omega naught capital T. Okay, so the j cancels out, and if you substitute omega naught with 2 pi over capital T, okay, then you have in the denominator pi k, and in the numerator sine of k omega naught t1. Okay, and then for k equal to 0, okay, so for k equal to 0, we have simply C0 that is equal to the average of the signal, right, over one period. Okay, and this is simply 2t1 over capital T. Okay. So if you compare with the result that we obtained, for example, 3.5, you will see that this is the same as we obtained there. Okay, so this is just an alternative derivation to example 3.5. Okay. Now, in this last example, we want to show that, just by specifying certain properties of this continuous time periodic signal, we often can, evaluate or find this signal explicitly. Okay. So here we're looking at the case where we are given 5 properties of this signal. Right? First of all, the signal is real. Okay. Secondly, the period is 4 with coefficient, with Fourier series coefficient AK. The third property is that AK is 0 for k greater than with absolute k greater than 1. So this basically means that there are only 3 non-zero Fourier series coefficients. Right? This basically means that only a minus 1, a0, and a1 are non-zero. Okay. Now, we know also by the fourth property that the signal with Fourier series coefficient bk, which is equal to this relation with ak, is an odd signal. Okay. And the last property tells us that the average of the signal power, okay, over one period is one half. Okay. Now we can look at these properties one by one. Right. So first of all, by the second property, we know that the signal has period t equal to 4. So this means that the fundamental frequency, which is 2 pi over t, is just pi over 2. Okay? And also, by property 3, okay, we know that there are only 3 non-zero Fourier series coefficients. So this means that x of t will be equal to a0 plus a1 times e to the j, okay, omega naught t, where omega naught is pi over 2, plus a sub minus 1 e to the minus j pi over 2 t. Okay. Now, furthermore, by the first property, we know that the signal x of t is real, right? So by 1, x of t is real, and thus, ak is equal to a minus k complex conjugate. Right. So this is saying that the signal must be conjugate symmetric. So if you apply this to A1, right, you will see that A sub minus 1 is just A1 complex conjugate. So if you substitute this property inside, this is saying that x of t is A0 plus this times its complex plus its complex conjugate, which gives you the real part of A1 e to the j pi over 2t, 2 times. Okay. Now we have used properties 1, 2, and 3, right? Now what about property 4? Property 4 is a little bit tricky. Okay. So now we're looking at a signal whose Fourier series coefficient is this e to the minus j pi k over 2 times a sub minus k. Okay. So if you first look at a sub minus k, right, what signal will have a Fourier series coefficient that is equal to a time reversal of the Fourier series coefficient of x of t? Okay. So we showed that this holds for the time reversal of the signal. Right. So here we showed that the time reversal of x of t has Fourier series coefficient a sub minus k. Okay. Okay. So a sub minus k corresponds to the Fourier series coefficient of the time reversal of x of t. Okay. And then e to the minus j pi k over 2, okay, is a phase shift in the Fourier series coefficient, which corresponds to a shift in time of the original signal. Okay. So by 4, we know that the signal corresponding to the Fourier series coefficient bk is this x of minus, right, the time reversal of t shifted by 1. Okay, so this minus t is inferred from this a sub minus k, and the time shift by 1 is inferred by this phase shift here. Okay, so if you get rid of this bracket inside, you have x of minus t plus 1. And property 4 tells us that this signal, x of minus t plus 1, is odd. Okay, and since x of t is real, this signal must be real as well. Okay, so this signal is real and odd. Okay. So if this signal is real and odd, then this means that the Fourier series coefficient must be purely imaginary and odd. Okay, so therefore bk must be purely imaginary and odd. Okay, so being odd implies that B0 must be 0, and that B1 is equal to minus B sub minus 1. Okay. Now moving on to the last property, right? The last property tells us that the average power over one period is 1 over 2. Okay. So by 5, okay, we know that the average power over one period, okay, which is also the average power of the time-shifted reversed signal, x of minus t plus 1 squared, okay, is equal to 1/2. Okay. So by Parseval's theorem, we know that the average power over one period is equal to the sum of the power of all of the harmonic components. Okay. So by Parseval's relation, okay, we know that B1 squared plus B minus 1 squared, which are the only two non-zero Fourier series coefficient for this delayed time reversal signal, is equal to 2 times B1 squared because it is odd, which is equal to 1/2. Okay. So this implies that B1 should either be J over 2 or minus J over 2, since it must be pure imaginary. Okay. Now, by this property 4, we can then, with B, we can then obtain the value of A. Okay. So by this property 4, we know that A1 should be e to the minus j pi over 2 b minus 1. Okay. And this term up here, right, is just minus j. Okay. So this is minus j b sub minus 1, and by the odd property of the coefficients b, this is also j b1. Okay, and similarly, a sub minus 1 is e to the j pi over 2 b1, which is j b1. Okay. So we know that a1 squared plus a minus 1 squared should be equal to 2 times b1 squared, right? So we're substituting these inside. We know that this is equal to 2 times b1 squared, which is equal to 1/2 by the above. Okay. But we also know that this, right, by Parseval's theorem, this 1/2 should also be equal to, the sum of the harmonic components. Okay. So this means that A0 is 0. Okay. Now there are two possible solutions for B1. Okay. So for B1 equal to j over 2, we have A1 equal to minus 1 over 2, okay, which is equal to A sub minus 1. Okay, and therefore, if you substitute this inside, you will get that inside the Fourier series representation, you will get x of t equal to minus 1/2 e to the j pi over 2t plus e to the minus j pi over 2t. Okay, and this is minus cosine of pi over 2t. Now, if you choose the solution of B1 equal to minus j over 2, then we have A1 equal to 1/2 equal to A sub minus 1. And in this case, x of t would be cosine pi over 2t. Okay. So in this example, we showed that by specifying certain properties of the signal and its Fourier series coefficients, we are able to infer what this signal is. Okay, and in this particular example, we can infer this signal up to a sign, up to a plus and minus sign. Okay. So again, going through this list, right? So we started out by looking at property 2, which tells us that the signal is periodic with period 4. Okay, so the fundamental frequency is pi over 2, and by 3, we know that there are only 3 non-zero. There can only be 3 non-zero Fourier series coefficients: a0, a1, and a minus 1. So x of t can be expressed in this form. So what remains to be determined is the coefficients for a0, the values for a0, a1, and a minus 1. Okay. Now, by property 1, we know that x of t is real, so the Fourier series coefficients are conjugate symmetric. So if you substitute this inside, x of t is equal to, can be written more concisely as this, right? So it's actually determined by only 2 coefficients, a0 and a1. Okay. Now, by this property 4, we know that a signal with Fourier series coefficient equal to this is odd. Now, what is this signal, right? So we see here that a signal with Fourier series coefficient a sub minus k should be the time reversal of the original signal x of t, and this further imposes a time shift. So the signal corresponding to this Fourier series coefficient should be x with the time reversal shifted by 1, or in other words, x of minus t plus 1. And we know that this signal is real and odd by this first and fourth property. So if the signal is real and odd, then its Fourier series coefficient must be purely imaginary and odd, which means that b0 must be 0 and b1 is equal to minus b sub minus 1. Okay. Now next, we still need to apply this last property, which is saying that the average power over one period is 1/2. Now, by Parseval's theorem, we know that this 1/2 should be equal to the sum of the Fourier series coefficients of b, and also should be the sum of the Fourier series coefficients of a. Okay. Now, we can see that the Fourier series coefficients of a1 and a minus 1 have energy already equal to 1/2, and therefore a0 must be 0. Right. So applying all these properties, plugging this inside either this equation or this equation here, we can find that x of t reduces to minus cosine pi over 2t if b1 is j over 2, and cosine pi over 2t if b1 is minus j over 2.